all of you. My research presentation topic is novel nano-based advanced technologies for the removal of hazardous radionuclides and heavy metal ions from groundwater. In this presentation, I will discuss 4 publications of mine. First, which is published in RSC Advances, second one is in MJC, and third one is in RSC Advances. And after explanation, I will go in second part, Journal of Membrane Science, which is published in 2020. As we all know, water contamination is a global issue. There are so many sources by which water is getting contaminated day by day, like domestic wastes, industrial wastes, agricultural wastes, or nuclear wastes. Dumping of huge radionuclide wastes and industrial wastes containing heavy metals in water stream raised global concern due to their global existence and severe toxicity. Due to its severe toxicity, high accumulation, and non-biodegradable tendency, it is severe environmental concern to remediate these hazardous contaminants like radionuclides and heavy metals from water. This slide representing the assessment data of uranium, chromium, cadmium, and various heavy metals and radionuclide ions. In literature, there are so many removal technologies are available like ion exchange, precipitation, coagulation, microbial bioremediation, but these found severe issues like high investment and running costs. Some technologies produce toxic slags, some technologies have high-tech operation and maintenance costs. So to view of the severe deterioration scenario of the water quality of various states of India, it is highly desirable for us to develop novel material-based technology to remove radionuclides and heavy metal ions from water. In literature, so many technologies, but I have chosen absorption technologies because of ease of operation, its simplicity, economically viability, and no involvement of any pre or post treatment. In commercially, there are so many available adsorbents also available in literature, and various studies are performed by use of activated alumina, ion exchange resin, clay, tops, and many more. But these adsorbents are having some problems like activated alumina produces toxic slag, ion exchange resin, high-tech operation is required. In the case of clay, high reaction time is required. In the case of top, chemically unstable. So I developed 5 types of advanced nanomaterials. First one is tributyl phosphate functionalized carbon nanotube. Second one is zero valent iron decorated carbon nanotube. Third one is thiofunctionalized carbon nanotube. Fourth one is iodide functionalized carbon nanotube, and the last one is cellophane functionalized activated carbon fibers. So basically, the matrix of all these materials are carbon nanotube and activated carbon fiber. Here the question arises: why I chosen carbon nanotubes? Because of its high radiation and thermal resistance, operates at wide range of pH. It is chemically stable and large surface area. And why I am choosing activated carbon fiber? Activated carbon fiber I purchased from Japan, and this is having large surface area, thermostable, and low acid and base reactivity. This slide presenting how I developed carbon nanotube in laboratory by using chemical vapor deposition technology. The main advantage of this method are as follows: there is no need to use explosive hydrogen during pyrolysis. I use nitrogen for the making of carbon nanotube. Cost-effective technology with large-scale production and the use of less toxic ferrocene as a floating catalyst, and the synthesis of carbon nanotubes I prepared without any substrate. After the development of carbon nanotube and pre-treatment of activated carbon fiber, various functionalization was done by various functionalizing agents to develop tributyl phosphate functionalized carbon nanotube, to develop zero valent iron decorated carbon nanotube. Third one is thiofunctionalized carbon nanotube, and the last one is iodide functionalized carbon nanotube. And this is the representation how I prepared cellophane functionalized activated carbon fiber. After the functionalization, these developed materials are applied for the removal of uranium and antimony, and found the removal efficiency very good. This representing the FTIR data of developed nanocomposites before and after removal of radionuclides. This is the experience data of ACH cellophane and CNP-TBP before and after removal of uranium. Here we can see uranium peak is observed. Here uranium peak is observed before and after removal of uranium. This is plain uranium activated carbon fiber. This is oxidized activated carbon fiber, doped uranium, and this is cellophane oxidized activated carbon fiber, doped uranium, which get high peaks of uranium. This is the experience data of zero valent decorated carbon nanotube, iodide functionalized carbon nanotube, thiode functionalized carbon nanotube before and after removal of antimony. It is evident from the experience and FTIR data that chemisorption takes place between contaminants and developed materials, which is responsible for the removal of contaminants from their corresponding developed materials. This is the recyclability studies. Now I am going to the second part of this presentation. Although the removal efficiency all these developed materials is very good, but these developed materials are used for the removal of single contaminant at a time, not simultaneously. So I proposed a plan to Department of Science and Technology to develop a novel material which can remediate a water from heavy metals from water simultaneously. For this case, I prepared two types of another nanoparticles, ferrous sulfide nanoparticles and carboxylic oxide ferroferric oxide nanoparticles by solvothermal method. After the synthesis of these advanced nanoparticles, these nanoparticles were doped inside the PVDF matrix. PVDF matrix I used and embedded these two types of nanoparticles in it. First, I prepared unmodified PVDF membrane having no any nanoparticles. Second one is in PVDF membrane having FES nanoparticle. Third one is PVDF membrane having second nanoparticle, which is carboxylic functionalized ferroferric oxide. And the last one is PVDF in which both nanoparticles are added. Characterization and membrane properties and separation efficiency of all these four membranes were evaluated and found that FES, CFFO, PVDF, both nanoparticles of membrane is highly efficient to remove multiple metal ions simultaneously from the water. This is the protocol of FES, CFFO, PVDF mixed matrix membrane. FES nanoparticle and CFFO nanoparticles are doped inside the PVDF and DMAC and PVP polyvinyl fiber dope. And by using phase inversion process, casting is done and dipping in a coagulation bar to prepare a membrane. This is the characterization of all these membranes, and in this characterization we can see no any visible agglomerates of nanoparticles inside the pore structure, indicating that nanoparticles were very well dispersed in the PVDF matrix prior to the casting. This is the AFM images of all these fabricated membranes. This is the simple PVDF having no any nanoparticles. We can see here roughness is around 67.2 because there is no doping of any nanoparticles. And in the case of B, we can see here roughness decreases after doping of single nanoparticle, which is FES. In the case of C, which is CFFO PVDF, in which roughness is again decreases from 48 to 30, and in the case of both nanoparticles embedded membrane, we can see here the roughness is 28.7, which is lower than all these three membranes. So we can see here decrease in roughness attributed due to the hydrophilic nanoparticles on the membrane surfaces. In general, higher surface roughness having tendency to getting fold. So in this case, both nanoparticles are added, so hydrophilicity is increases. Due to the high hydrophilicity, folding effect will be lesser. So we can evaluate that all fabricated membranes have also ability to prevent from the addition of unwanted particles on the surface due to the continuous decrement of roughness. This is the FTIR spectra and water uptake capacity of unmodified PVDF and nanoparticles embedded membranes. With increase in hydrophilic site present on the membrane surface affinity of the membrane towards water increases, thus more will be the water uptake on the membrane surface and less will be the contact angle. Here we can, next slide we can see this contact angle study. By loading of nanoparticles, voids and cavities are formed between nanoparticles and the PVDF matrix due to heterogeneity, which increases the amount of water content, leads to the higher water uptake capacity. This is the reason behind it. This study shows the water contact angle. This is the mechanical and chemical study, chemical stability study. And this is the permeation performance of the fabricated membrane. Here we can see FeS-CFO4 nanoparticle doped PVDF membrane having low contact angle. Due to low contact angle, flux will be high. So we can see here the unmodified PVDF having high hydrophobicity. Due to the high hydrophobicity, water uptake capacity of permeation performance or water flux is very low. Or in the case of FeS-CFO4 PVDF, in which both nanoparticles are added, flux is very high in comparison to all these three membranes. So we can conclude this: the enhanced permeability of the fabricated membranes is consistent with the water uptake, contact angle, porosity, and membrane morphology parameters. Loading of different types of hydrophilic nanoparticles like carboxylic puncturized hydrophilic oxide nanoparticles enhances the hydrophilicity of the PVDF membrane due to the elevation of hydrogen bond interaction between water molecule and surface of the membrane. By incorporation of hydrophilic nanoparticles, the dense polymeric chain packaging is obstructed, introducing more free volume for water molecules passing through. This is the separation performance of fabricated membranes. FeS-PVDF membrane was examined only for the rejection of chromium. Second one is examined for the rejection of cadmium and lead, and the last one is for the simultaneous rejection of cadmium, lead, and chromium. These are the reaction mechanisms. And this serves one. The applicability of this membrane is applied in neutral as well as in acidic pH. In acidic pH, in neutral pH, FeOH and COOH present in its ionized form, responsible for the negative charge on the membrane. In acidic form, protonated form will be generated. So due to this, positive and negative charge generated on the membrane, positive and negative charge species will be, some species will be absorbed and some species will be rejected. That's why the absorption that's why the overall separation takes place. And then this membrane is applicable for the treatment of groundwater contaminated with hazardous heavy metals. For this, I used the industrial area, water of industrial area of Kanpur, Jajmau and Rania, and study concluded a single step filtration of this contaminated water through developed membrane. It was observed that developed membrane is highly efficient to bringing down the concentration of multiple heavy metals to WHO limit. This is the evidence of the interaction between fabricated membranes and the metal ions using XPS. We can see here curve-fitted high-resolution scans of FeS-CFO4 PVDF membrane after filtration of metal ions for chromium, cadmium, and lead. We can see here after filtration we study the XPS, which evidence that chromium is separated out, cadmium is separated out, and lead is separated out. So we can see here interaction of chromium, lead, and cadmium onto FeS-CFO PVDF is validated and evident from the appearance of double peak of chromium 2p 3/2 and chromium 2p 1/2 and double peak of cadmium 3d 5/2 and cadmium 3d 3/2 and lead and so on. Additionally, splitting of multiple peaks are observed for the 2p 3/2. This is two peaks are separated, which suggests that the reduction of chromium 6 to chromium 3 from FeS nanoparticles Fe2 plus and S2 plus play a key role in the reduction of hexavalent chromium. And finally, I acknowledge Professor Jayant Kumar Singh of Department of Chemical Engineering, IIT Kanpur, Professor Jaya Dwivedi ma'am, Vanastali University, Dr. Nalini Shankar ma'am, IIT Kanpur, and I highly acknowledge Department of Science and Technology for DST Young Scientist Award, and warm thanks to all group members for their cooperation and kind support. Thank you so much.
Madam, Yeah. Actually, very good to the presentation. Actually, just a small question. So, did you compare your membrane with the commercial membrane?
No, sir. Actually, there is a problem behind it. I published the paper in Journal of Membrane Science, but here the problem in this study actually chromium lead and another one is what? Cadmium, lead, and chromium. Three species are rejected from.
And
But
did you try for dye removal or
हाँ
any other
ये मेरा
organic-
फ्यूचर वर्क है सर कि मैं फ्यूचर में इन सबको
organic
हाँ वो मैं देख लूँ उसमें वही मेरा फ्यूचर प्लान है इसके बारे में और क्रॉस प्रोफिटेशन के बाद के द्वारा मैंने इसको परफॉर्म किया हाँ यस सर मैंने दिखाया उसको
Thank you very much. Now this session is over. Now we will again meet after tea break.
Sir, tea break.
Oh yeah.
Let us have a quick tea break for 5 minutes, just 5 minutes, please. Please come back in 5 minutes so that we can have more fantastic speakers.
I